welcome to our next topic, which today's is instantaneous rate of change. We're kind of done learning about limits. Now we're going to transition into actual calculus by being able to apply those limits to topics that we've talked about in previous courses, but we're going to mix in the limit stuff alongside to turn it into calculus. So in calculus, one of our early goals is to be able to describe how a function is changing at a given value of x. This is referred to as the instantaneous rate of change. This task is very difficult with most functions because curves don't have a constant rate of change like a linear function does. So linear functions are the only functions you guys have ever seen that actually have a constant rate of change. That's what gives it that linear shape, is that between any 2 points, if you were to calculate the rise over the run between those 2 points and find the simplified version of that ratio, no matter what 2 points you pick, it always equates to the same ratio. But with curves, the distinct difference is curves change their rate of change. From any 2 points, they're going to have different rates of change between them. Take bigger jumps, or the curve increases more quickly or more slowly, and they flatten out. Curves can do all kinds of things, and that's where our focus is going to be for the next several sections of the course, is being able to really describe and focus in on coming up with equations or patterns that describe that rate of change on a curve. So what we begin with is the process of to begin to try and find the instantaneous rate of change. We begin that process by estimating it with an average rate of change. So you guys have heard this phrase average rate of change before in the past. We just haven't focused in on it, or really done a deep dive on average rate of change and the implications that it has. So to begin with, we use a secant line. So you've heard that word before in geometry. It's a line that passes through a curve at 2 points. And that's exactly what we're going to do here. We are going to take a curve, and if I want to try and estimate how that curve is changing at that point, well, I can take 2 points near that desired value and draw a line that passes through those two and find the slope of that secant line and use it as an estimate for the actual slope at the desired point. So that's the idea of a secant line. So when you think of secant line, you need to think of 2 points. It is a line that passes through the curve at 2 points. So when we do this, what we're really trying to determine is how that curve is changing over an entire interval of x values rather than just one. So again, that's the idea. We're using the average rate of change over an interval to estimate the instantaneous rate of change, as long as the interval that we pick contains the value of x that we are trying to find the instantaneous rate of change for. For example, if I wanted to know the average rate of change at this point, or excuse me, the instantaneous rate of change at this point, it wouldn't make any sense to pick these 2 points to draw my secant line, because how the curve changes over that interval, the curve is a lot steeper on this part of the curve than it is back here. So we always want to make sure that the interval that we choose includes the point that we want to learn about. Now, sometimes that point will be an endpoint for the interval. Sometimes it's just somewhere in between the endpoints. There's no set rule on how we go about doing that for the time being. So we just need to make sure that it's in there somewhere. So the good news is, to calculate the average rate of change, it's math that you guys have done before. Finding average rate of change is really just finding the slope of a line that passes through 2 points. So you've seen this written a whole bunch of different ways in the past. Y2 minus y1 over x2 minus x1, change in y over change in x, rise over run. There's all different ways to describe this, but mathematically, it's all the same. You are finding slope of a line. So there are 2 ways that we could represent this slope formula. The more traditional way, f of b minus f of a over b minus a, that kind of equates it to the old school y2, y1, x2, x1 formula. We're just using function notation for a given function f of x over our interval from a to b. So this is probably the easiest way for you to wrap your head around it. But an alternative way that's going to become more important to us here in a little bit is this guy. So rather than using both a and b, what we can really say is my interval stretches from A and then to an endpoint B. But to get to that endpoint, I start with my first endpoint and I add something on to that. So that H value, or other times you may see it written as delta X or change in X, is really just the length of the interval or the distance on the X axis from A to B. So again, another way of interpreting it, here's A, here's B. So to get to B, I am adding H units on to A. That's why I can write this as A plus H. So if I do it that way, if I use A plus H in place of my B value, then I would have F of A plus H minus F of A. And the denominator, well, if I take A plus H and I subtract A from it, again, this is like my B minus A, then these A's cancel out and just leaves me with H in that denominator. So this is an alternative form for representing that slope of that secant line. Again, this is going to become more important to us here in a few minutes. So let us try an example. So I have this quadratic function, x squared minus 2, and my goal here is to estimate the average rate of change for this function over the given interval from 0 to 3. So you can see on this graph, I already have my points plotted at 0 over 3. So just in general, if I were to look at this graph, over the course of that interval, this graph is always increasing. So remember, lines that increase, this linear or this secant line is also increasing. Things that increase have positive rates of change. So this line, the secant line, has some kind of positive rate of change. That's what we're going to calculate. But if you look at this whole interval, there's an extra point plotted on here, and that's kind of our focal point. It just kind of is holding the place of some point in this interval, 0 to 3. So if you keep in mind that our goal is to try and approximate the actual instantaneous rate of change at that point, then this line in this interval can serve as an estimate to the start of that process. Okay, so just keep that framework in your mind as we go through this. So to do this, again, average rate of change or slope of my secant line. I'm actually going to show it to you using both forms that we just covered here. So for the first guy, our f of b would be f of 3. Again, this is my interval 0 to 3, so that's from a to b. Or in this term, or in these terms, my h value would be 3. That's the distance that I have to add on to my a value to get to b. So for f of b, that would be f of 3 minus f of a, or f of 0, over b minus a. So now I have to evaluate f of 3 and f of 0. So if I plug 3 in, I get 9 minus 2, or 7. And then if I plug 0 in, I get negative 2. So that's where I ended up, and that's the y value I started at. And then over 3 minus 0. So we end up with 9 over 3, or an average rate of change of 3. So in this context, there is no real world meaning behind this, but what we're working towards is being able to take these functions that actually do represent real life quantities and using them to interpret real life quantities of change. So let's say, for example, f of x represents the profit of a company in thousands of dollars, and our x values represents let's say weeks, so 0 to 3 weeks. Well, if that's what our units represented, then when we find this average rate of change, we can actually apply the units. So what all of these numbers would mean is after 3 weeks, the company's profit is $7,000. And at the very beginning, they were actually negative $2,000 in the hole. So they actually owed money to someone. But looking at the change over that interval, overall, the company's profit increased $9,000 over the course of 3 weeks for an average rate of change of going up by $3,000 per week. So that's the idea of an average rate of change. We're looking at what's the total amount of change over a given interval of time. So keeping that in mind, that is a rough estimate of how this function changes for just about any point over the course of this interval. Now, for some points, it's going to be way off from what it really is. Other times, it's going to be pretty close to what it is. There could be a moment in time where it's exactly what it is. But the idea is we're taking into account all of the changes over the course of the interval, and this is a good representative for that amount of change. Okay. Now let's look at it in the other form. So for this one, instead of f of b, we're going to represent that slightly differently as a plus h. So my a value is 0 plus 3 minus f of 0 all over my h value, which is 3. So realistically, the notation is what's changing. 0 plus 3 is still just 3, so I would still be plugging 3 in, and I'm going to get all of the same values here. The only difference is in the bottom, I don't necessarily have to write minus my a value, and the end result is still going to be the same thing. Still going to represent that we're increasing by $3,000 per week if we had those real life units on there. But that's the idea here. So average rate of change is just plugging in or finding the slope through 2 points on the curve in an attempt to try and estimate the exact instantaneous rate of change of the function at a particular point. All right, so let's try a couple more of these. This would be a good idea if you guys are watching the video to pause and try these two problems on your own, and then you can check back in when you're done with me to see how you guys did. All right, so let's check this out. So my A and B values would be 2 and 5. My H, if you wanted to write it out that way, in this case would be 3. So my slope of my secant line, or my average rate of change, would be f of 5 minus f of 2 over 5 minus 2. Or if you chose to write it the other fashion, f of 2 plus 3 minus f of 2 all over h is 3. Again, they essentially are equivalent to each other. 2 plus 3 is the same as 5. 5 minus 2 is the same as 3. So just different ways of setting it up. Either way, I need to know my value of f of 5. So plugging 5 in here gives me 8 over 4, or 2. Plugging 2 in gives me 5 over 1, or 5. So we end up with negative 3 divided by 3, or negative 1. And again, if there was a real life context, we would take our y units divided by our x units to show that it is a rate of change. Again, we're interpreting that over this interval, this is how the y values change on average as x changes by 1 unit. Okay, and for the second one, same idea. So let's find the slope of the secant line. So this would be g of 3 minus g of negative 2 all over 3 minus negative 2, or those a and b values are 5 units apart. So we could really say g of negative 2 plus 5 minus g of negative 2 over 5. So either way, g of 3, I would need to substitute that in. So that's going to give me 27 minus 12 plus 2, or 17, minus, plug negative 2 in, that gives me negative 8 plus 8 plus 2. So we get positive 2. And then on bottom, we've got 5. So 15 divided by 5, or an average rate of change of 3 units. So now that you've seen a couple examples of how we calculate the average rate of change, now we're going to try and extend it. So in order to make an average rate of change estimate better, we just have to make the width of the interval surrounding our value of x smaller and smaller. Or another way of saying that is making that or approach 0. So again, visually, this is a pretty easy concept to understand. If I want to try and estimate how the curve is changing at that exact point, well, I could really pick any two x values that I want to that surround that. So this would not be a good idea, but if somebody wanted to, you could use those 2 points. Wow, I really missed the mark there. You could use those 2 points to estimate it because those 2 points have our desired point in the middle of them. But that line, you can see the shape of, or the steepness of that line does not do an accurate job of reflecting how the curve is changing at that exact point. You can see the curve is much steeper than that line. This line almost has a slope of 0. It's very flat. So the best way to make an estimate more accurate is to scoot these 2 points closer and closer. The closer these 2 points get, let's say I pass through these two, now that's a good bit better. It's still not great. This is still going to be much steeper than these two are. But as you scoot these 2 points closer and closer to one another, now we're getting steeper and steeper. And eventually, what's going to happen is as those 2 points get closer and closer, their difference is going to be so small that we represent it as saying h is approaching zero, or an infinitesimally small value. So as that interval gets smaller and smaller and smaller, the line, which is still technically a secant line, that secant line slope will transition from the average rate of change to the instantaneous rate of change. And in doing so, because the 2 points are so close together, or so close to one another, we essentially can't really tell a difference between them anymore. So instead of a line passing through 2 points that are really close to one another, they're basically on top of each other. So instead of using what we call a secant line, we are transitioning to a tangent line. So a tangent line, if you remember back to geometry when you guys talked about circles, well, that was pretty good. A tangent is any line that passes through one point on a curve. So if we put all of this together, it leads us to our goal, which is to be able to find the instantaneous rate of change of a function. So that instantaneous rate of change of a curve refers to the slope of a curve at a specific value of x. So at one point, or the point of tangency, what is the exact rate of change of the curve in that one exact moment of time? Good analogy for this is if you're driving, your car has a speedometer inside. At any given moment of time, that speedometer arm is pointing at the exact speed of the car at that moment. But because your speed is constantly changing in a car, it's hard to know at an exact moment what the speed is. But if you were to take a picture of your speedometer for that one split moment in time, that picture will read exactly what the car's speed was for one split moment in time, and then it's gone, and it's going to be slightly different. So this value is found by finding the slope of that tangent line that passes through the 1 point on the curve. The process of transitioning us from a secant line that goes through 2 points and average rate of change through those 2 points to a tangent line and the instantaneous rate of change requires us to apply a limit. Because again, the idea is when we transition from 2 points that are far apart or across an interval, the only way we do that is by scooting the 2 points closer to one another. So as they get closer, the real slope is going to be revealed, and we know exactly how that line is changing. When the two lines are so close to one another, it basically looks like 1 point. But all of that is controlled by our h value, that distance between the 2 points, or the length of the interval. So what we can do is force that change, or excuse me, that distance to approach zero, which is going to in turn force the 2 points together. So what that does is it takes a non-calculus topic like slope, we can mix in some limits to it, and now we have created a calculus process. So our formulas: to calculate the instantaneous rate of change of a function at a value of x equals a, or to find the slope of a tangent line that passes through the point on the curve where x equals a, we have two forms of that process. The first is controlled by h. So the limit as h approaches zero of, if you look at this, this is that same exact slope formula from earlier. The only difference now is we're taking the limit of it as h approaches a particular value. Or our alternate form is using the other form, so the original slope formula. So in this case, instead of controlling the distance by making h go to zero, we actually just keep one endpoint stuck and we scoot the other one closer to it. So if you look at it, we have our fixed point where we want to know the rate of change, which is x equals a and y would be f of a. And the second point, our b value, where we're just going to scoot that point closer and closer to a. So for that alternative notation, that's why we have as x approaches a. So basically, we're just going to make this guy get closer and closer to the first one. So when we use all of our different methods for evaluating limits that we've learned up to this point, to try and find the value of these, that is what's going to allow us to actually calculate the instantaneous rate of change at a particular value. So which one we use is really just dependent upon which one we're given. If we have a preference, it's actually easier to use this H form, even though when finding average rate of change, it's easier to use the standard slope formula. For our purposes, it's actually a good bit easier just to stick with the H form of this limit definition. So let's try some. So I want to find the instantaneous rate of change of the function f of x equals x squared minus 2 at x equals 2. So let's do that. So instantaneous rate of change, or slope of the tangent line, is equal to the limit as h approaches 0 of f of, so my a value in this case is that 2. So 2 plus h minus f of 2 over h. So that's the definition that we had a second ago. So always begin with that, and then this notation actually informs the process. So to evaluate this, we need to actually come up with an expression for f of 2 plus h. So the limit as h approaches 0. Yes, we need to keep this limit operator on this at all times, otherwise it loses all of its meaning. So f of 2 plus h, remember that this location inside these parentheses is telling us what to substitute into the function f of x. So we need to take the expression 2 plus h and substitute in for x, which would give us 2 plus h quantity squared minus 2. All of that is the value of f of 2 plus h. And then minus f of 2, well, if I plug 2 in, I get 4 minus 2, or 2, all over h. Now we need to try and take the limit. If I were to evaluate this limit right now at h equals 0, when I plug 0 in, I would get 2 squared is 4, minus 2 gives me 0, and h turns into 0 on the bottom. That's the indeterminate form. And that will always happen with the first attempt of direct substitution when taking the limit of this expression. That's because there's stuff in here that needs to be canceled out and simplified. We're not done. We need to do some algebraic simplifications with this expression. So the first thing I'm going to do is expand this binomial squared. So that is going to leave us with 4 plus 4h plus h squared, if I do square double square on that, and then minus 4, because that's what these two combine to be, divided by h. So now if you look at this, when we do this process correctly, anything in the numerator that does not have a factor of h will cancel each other out, so that everything remaining has a factor of h, which then can reduce out with the h in the denominator. So I'm going to factor out cancel out a factor of h from every term in the numerator and the denominator, which results in the limit as h approaches 0 of the expression 4 plus h. That expression I can now take the limit of using direct substitution. And if I do so, the limit of 4 plus h as h approaches 0 is simply 4. That value is the instantaneous rate of, yikes, I don't know what happened there, the instantaneous rate of change of f of x at x equals 2. Or another way of saying that, this is the slope of the tangent line at x, or of f of x at x equals 2. So if I graph that function x squared minus 2, and I draw that tangent line, if I go back up here, this is actually the equation of this graph. The parabola here is x squared minus 2. This is the tangent line at x equals 2. The slope of this line is 2. So that is exactly the rate of change of this curve at that exact point. If we move from that point, because it's a curve, every point on a curve, the slope is going to change just slightly. So right after that, x equals 2, it's going to be a little bit steeper than that. So the slope is going to be slightly more than 2. So that's the idea. Curve is a way of expressing the idea that the rate of change is changing. So as the curve is getting steeper, the rate of change of the curve is getting bigger, and so on. So what we just learned was how we can evaluate or calculate the rate of change of a function at a particular value of x. And it's through this limit process. But if you think about what we also talked about, the idea of a curve is constantly changing its rate of change. Every new point that we shift to is going to have a new rate of change. That means to know all of the different rates of change, we would have to use this limit process for every single possible value of x on a given function's graph, and that would take forever, literally. So we don't want to go about it doing it that way. So instead, what we can do is notice some patterns and trends and use that to kind of inform our next step. So if you were to simply just look at this function, it does look like there are some noticeable trends. This quadratic function is decreasing. At one point, when we change directions, we would have had to come to a stop, which means we would have had a rate of change of 0, and then it begins to increase again. So if we go from negative slope to 0 to positive slope, that's a pretty noticeable trend. And on top of that, we can also think about the idea of steepness. As we move towards negative infinity, this graph is going to get steeper in the negative direction, so big negative slopes. And as we work towards this turning point, it looks like the graph is going to be flattening out. So this graph won't be as flat, or will be flatter here than it is up top here. Or if we were to look down here at the bottom to draw a tangent line, it would have to be perfectly flat. And then as we move past, we would grow steeper and steeper and steeper, which means the slopes are changing in a particular fashion. So whenever we notice those patterns within numbers, we can try to create some kind of function or equation to actually represent that pattern. And that is the idea of a derivative. So the big thing that we're going to talk about the rest of this section, and really the rest of the course, is the idea of a derivative of a function. So as a function's curve twists and turns, its rate of change is changing. So at each different value of x, it will have a different rate of change. And when we look at all of these rates of change together, they're going to form a pattern, which we can write a function to represent. That function is called the derivative. Notationally, if the original function is named f of x, then its derivative function is represented with the notation of f with a little apostrophe tick mark after it, and then the parentheses with x inside, but we read that as f prime of x, or the derivative of f of x. So for this function, it's important to know the inputs and the outputs, like how the function actually works. So just like with any other function, your inputs are x values that you can plug in and do the math that you need to in the equation, and then the outputs are the results of that. But for the derivative function, your inputs are still going to be values of x, but specifically they are values of x where the original function f of x has a rate of change. And now that might sound kind of redundant, but there are some points on some graphs that there are no rates of change. So let's think of some of those possibilities. So one easy one to think of is a function with a hole. So if a function has a hole on it, then the function itself, the original function of f, isn't even defined at that value of x. So if there's no point there, then there's no way it has a rate of change there. So that would be a value of x that we would not include in the input of f prime. Another example, vertical asymptotes. So another case where the function would be undefined. If there are no points on the graph at a particular value of x, then there's no way for us to describe how it's changing there because the graph doesn't exist. Other situations would be places where a graph changes at in unnatural ways. For example, a sharp turn. So a place where certain functions actually change direction in a sharp fashion, where we instantaneously switch from decreasing to increasing without coming to a natural stop first. That would be like a car driving forward and then all of a sudden it backing up without ever having to step foot on the brake and slow down first. That just can't happen. There are other graphs that have places where a tangent line would actually go vertical for a second, which would mean a slope of infinity, and that's just not something that we can actually have. So there are all kinds of different ways that graphs do not actually have rates of change. So what we have to identify is what values of x does the graph have a slope at or a rate of change, and those are the only values of x that we can use to substitute into our derivative function. So once we know those, then we can pick any of those, plug them into this equation, and the output, or the y values of f prime, these are going to be the slopes of the tangent line, or the slopes of lines tangent to f of x at these x values. So again, the idea is going to be, we're going to have a function f of x, some curve, and I want to know the slope of f of x at a particular value of x. So we simply find the tangent line, and then we can use this limit process to find the slope of that line, which is the exact same as the slope of the curve. So it's kind of a paired process. Finding the slope of a tangent line is the same thing as finding the value of this derivative or finding the slope of the original function. So all of this goes together. So when you're going to hear these names mixed together a lot, and you have to understand that they all kind of represent the same thing. So the derivative of a function is some kind of new function. It gives the slope of the line tangent or the slope of the original function at any value of x where that graph has a tangent line. So that's the idea. All of these three things are kind of tied together. So notationally, you may, or even in reference by name, you may hear them referred to in many different ways. So we could say the value of f prime of c. We could write it as the slope of the tangent line. We could refer to it as the slope of f. We could even refer to it as instantaneous rate of change. All four of those really are talking about the exact same thing. So again, to come up with the actual equation. So again, we have this process that we just did with this previous example, where if I want to find the slope of a function at one value of x, I can just do this process one time, actually putting the number in there. But if my ultimate goal is to know the slope or the rate of change at any value of x, I wouldn't want to do this over and over again. So instead, we take that exact same process and we simply leave x in its place. Because x can represent an entire set of unknown values, or the domain of the function, by leaving x in there, it just means that when I do this limit process, instead of getting a number at the end, we'll have a expression that has x inside of it. And that's how we're going to get our derivative function. So this is called the limit definition of a derivative. So this says that f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. Or we have this alternative form of that as well, using that alternate form of slope. So either one that we work with, they represent the same thing. We're going to do that limit process, but keeping x in there, so our end result is an expression of x. When we do that, once I have the equation, then we could pick any value of x that we want to afterwards and simply plug it in to this new function, and it would give me the same result as doing this limit process over and over and over again for all those different values. So instead of having to do the limit process multiple times, we do it one time to get the equation, then we can plug in any numbers that we want to. So the most common notation for derivatives is this f prime notation. There are other systems as well. Again, there are two mathematicians who are credited with discovering systems of calculus, but they did so independently. That's Isaac Newton and Gottfried Leibniz. Newton preferred this f prime notation. The dy dx is a notation that is from Leibniz's system, and modern calculus, we've kind of melded the two together. So dy dx, if you think about it, that is very similar to delta x over delta y over delta x, or change in y over change in x. And that's because that's what a derivative represents. It's the instantaneous rate of change in y over the instantaneous rate of change of x. Other acceptable notations, y prime. This notation, d dx of a function is really a operator. It's a way of saying I want to find the derivative of this thing inside. Same thing here. I want to find the derivative of this thing inside with respect to a particular variable. So we will really be focused or using these first three more than these other guys. This one will pop up every so often, but it's more for defining rules than when we are actually doing our work. So let's dive in and actually try one of these guys. So I want to find the derivative of the function f of x equals 3x squared plus 2x plus 1. So that's my goal. And after I find that derivative equation, then we will use it to answer the second part. But when the directions say find the derivative of, your goal is to find f prime of x as a function of x. So this can't just be a number. It needs to be a function of x. Okay, so let's do that. F prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. So if you look at that notation, that is the exact same thing that I wrote down at the beginning of the last example when we were trying to find the actual value of slope at a particular point. The only difference is instead of a being in there, we have just a placeholder for x. Again, we have to have that in there if we want the end result to be an expression of x. So just like the last time, we actually evaluate this first guy. I'm going to do the same thing. So I'm going to take x plus h and substitute it into the function of f of x anywhere that x shows up. So in this case, there are two places where that happens. So my result is the limit as h approaches 0 of 3 times x plus h quantity squared plus 2 times x plus h plus 1. That whole expression is the result of f of x plus h. Then I'm going to subtract from it the value of f of x. Well, f of x is the original function. So 3x squared plus 2x plus 1. Anytime that your original function is more than one term, make sure that you have parentheses around it so that you remember to distribute that negative inside to everything. So now let's clean this up a little bit and expand and simplify this result. So we've got the limit as h approaches 0 of, so we need to expand this. Again, square double square would give us x squared plus 2xh plus h squared. Then I'm going to go ahead and distribute the 3 to all of that. So that would give me 3x squared plus 6xh plus 3h squared. Then distribute the 2 inside of here. So we have 2x plus 2h, and then plus 1. And then let's distribute the negative down into the second group. So minus 3x squared minus 2x minus 1, all over h. Now, earlier when we did this with just numeric values, I told you that anything in the numerator that didn't have a factor of h automatically has to cancel away, because if it doesn't, then there's no way for us to actually take this limit. Because as of right now, if I try direct substitution in here, all of the h stuff disappears, all of the non-h stuff cancels each other out. So the numerator is 0, the denominator is 0. So the only way for this process to work is for us to cancel out all of the non-x factors, or excuse me, terms. So 3x squared, negative 3x squared, has an h, 2x and negative 2x, has an h, 1 and negative 1. By canceling all of those factors out, everything that remains has a factor of h, which we can reduce with the denominator and then take the limit. So a factor of h from all of these remaining terms and the denominator leaves us with the result that f prime is equal to the limit as h approaches 0 of the expression 6x plus 3h plus 2. Now I can take this derivative, or excuse me, evaluate this limit, because h is the variable that we're controlling. So even though there's an x in here, that is just treated as a constant within this expression. Or what that means is that part doesn't change. The constant doesn't change. The only thing that can change its value is the term with h in it. So when we plug 0 into that, that term disappears, and our final result is the expression 6x plus 2. Or the derivative of f of x, or f prime of x, is equal to 6x plus 2. That means if you take any value of x from the original function and plug it in to f prime, the result is how the original function is changing at that given point on the graph. So let's do that. They gave us two values of x here to evaluate. So f prime of 3 would be equal to 6 times 3 plus 2, or 20. So that means on this graph, if I were to create the tangent line, that line has a slope of 20 units at the point x equals 3 on this graph. Or if I try it for the next one, f prime of 4 would be 6 times 4 plus 2 is 26. So just from that piece of information, it kind of lines up with what we know about a quadratic function's curve. So I don't know exactly where this graph lies, where its zeros and everything are, but I know that it opens up and it has a y-intercept of 2, of 1. So just a rough sketch. All I care about right now is the idea that when x is 3, it has a slope of 20, so pretty steep. But when we get to x equals 4, it's even steeper. Now it has a slope of 26, and that kind of is reinforced by the idea of these curves that as this parabola continues to the right, it is going to continue getting steeper and steeper and steeper, or its slope or instantaneous rate of change is going to get bigger and bigger and bigger. So again, that is what this function does. It tells us the slope of the graph of f, or the slope of the tangent line to f, or the instantaneous rate of change of f of x. That is the purpose of this derivative function. All right, so let's try another one. Now, this one's a little bit more complicated. So it's same goal. I want to find the derivative, find f of prime for the original function f of x equals square root of x. Then we're going to use it to find the slopes at these different points. So the reason that this guy is, or we're going to have issues here, is not because this original function is complicated. It's because of the limit process. But the process does not change. I have f prime of x equals the limit as h approaches 0 of f of x plus h minus f of x over h. Again, I would always recommend that you begin this process by writing out the limit definition and then using that as a reminder to how we set up the next step. So I'm going to take x plus h, substitute it in for x into f of x. So that would yield square root of x plus h minus square root of x all over h. And again, no matter what the form of f of x is, if you start right off the bat with direct substitution, you're always going to get the indeterminate form 0 over 0. Same thing here. I would plugging 0 in for h would give me root of x minus square root of x, which is 0 over 0. So this is one of those problems from a few sections ago where we have to rationalize the numerator. So we're going to multiply top and bottom of this guy by the conjugate pair of this numerator, which would be square root of x plus h plus the square root of x on top and bottom. So by doing it to the numerator, remember that creates a difference of squares situation. So we get the first term squared, or x plus h, minus the second term squared, or just x. And then on bottom, I'm not going to distribute. I'm going to leave that guy alone because of what's going to happen here in a second. So we have that conjugate pair in the denominator now. So now when I go to clean this up, again, just like before with the polynomial, our non-h stuff has to cancel out in the numerator. So x and negative x cancel, which just leaves an h factor in the numerator, which is going to cancel out with the h factor in the denominator. So since everything canceled out in the numerator, what's really left behind is just a 1. So my derivative f prime of x is equal to the limit as h approaches 0 of the expression 1 over square root of x plus h plus square root of x. Again, once we fix the expression, then we can try direct substitution again. And when I do that, if I plug 0 in here for h, it just becomes square root of x again. So my final result is actually 1 over square root of x plus square root of x, or 1 over 2 square roots of x. So that is the equation for f prime, 1 over 2 square roots of x. So now that I have that guy, now I can go to these points and tell you exactly what the slope of the tangent line is going to be at those particular values of x. So for example, f prime of 1 would be 1 over 2 square roots of 1, or 1/2. And f prime of 4 would be 1 over 2 square roots of 4, or 1/4. I want to do one more point just to kind of reinforce something I'm going to show you on the graph here in a second. Let's say I wanted to pick a big value of x, like 100. If I plugged 100 in there, I would get 1 over 2 square roots of 100, or 1/20. So I want you to notice what's happening to the value of these slopes. As x gets progressively bigger, 1, 4, 100, the value of slope is getting smaller, 1/2, 1/4, 1/20. And if you remember what the graph of square root of x looks like, it starts at the origin, and then it's this springboard guy. Remember, it's the top half of a sideways parabola. So the reason I mention what's happening to these slopes is because parabolas grow steeper as you move to the right, but this is a mirror image over that line y equals x, so this guy is actually getting flatter as we go to the right. And you can see that by looking at these slopes. If I continue to plug in bigger and bigger values of x, eventually that slope is going to approach 0. It's going to get really, really small, really flat. Now, the second part of this is it tells us to discuss the behavior of f at 0, 0. Well, let's say that I wanted to evaluate f prime of 0, because again, if I'm talking about derivatives and slope, let's try and figure out what that value is. That would ask me to find 1 over 2 square roots of 0, or 1 over 0. And up until this point, you guys have always approached an expression like that as calling it undefined, which is okay. I mean, technically that's true. Now, we can't divide by 0. That's one of the golden rules of mathematics. But with our calculus mindset that we now have, instead of thinking that as undefined, I want you to really think about what that's asking us to do. So as x gets closer and closer to 0, the value of that denominator is also going to get closer and closer to 0. So as we approach 0, though, it's not going to equal, it's just also going to get closer. So instead of thinking of this as 1 divided by 0, I want you to think of it as 1 divided by numbers that are smaller and smaller and smaller. So when we do that, when we take a number, a fixed constant, divided by smaller and smaller pieces, this is actually going to approach infinity. So what that means in terms of this graph is as x gets closer and closer to the origin, that curve is actually going to get steeper and steeper and steeper. Now, my sketch doesn't do a great job of showing this, but if I show you the square root of x, this function, let me make this look a little bit better. Desmos does a much better job of showing this. You guys can see. Now, I'm not zoomed in all that close. It's small to our typical standards, but I can keep zooming in a lot farther. And all that's going to happen, you guys are going to see that this graph is just going to continue to get steeper and steeper and steeper until it essentially just looks like a flat line. Eventually, this is going to take up my whole screen. It's just going to look like a straight vertical line instead of the curve that it actually is. And that is just kind of reinforcing the idea that as we move back towards that point, because the slope is growing vertical, or excuse me, the tangent line is growing vertical, the slope is heading towards infinity. And that is why, that is why we can't actually, there we go, we can't actually evaluate the value of f prime at x equals 0, because technically it doesn't have a slope. Its slope is infinite. So as we work back towards that endpoint, we're getting steeper and steeper and steeper, or that slope is approaching infinity. Now that we know how to find the derivative of a function, now we can actually find the slope of any tangent line that we want to any function for any value of x. So once we have that skill, we can also then create the entire equation of the tangent line. So if we wanted to be able to graph the function and the tangent line together, which is useful for a lot of different processes that we'll do throughout the course, we can actually find the full equation of the line and be able to graph both of those. So we're going to do that for this guy here. So we've got f of x equals x squared plus 3x minus 1. So we want to find the equation of a tangent line for that function at the value x equals 2. So you guys have worked with linear functions a lot throughout your other courses. You're probably most familiar with slope-intercept form, y equals mx plus b, but we're actually going to use an alternate form for a linear function called point slope, because it has the added benefit of not needing to know the y-intercept right off the bat. We can just start with any point that the function passes through. So when we write this, our point that we use to create this is going to be our point of tangency. So I gave you that value of x equals 2. We know that that is where we want the function to be tangent to the line. So to find the y-coordinate at that point, we just simply plug that in. So if you're not told the y value, that'll be the first thing we have to take care of here. So I'm going to plug 2 in. It gives me 4 plus 6 minus 1, so 9. So 2, 9 is the coordinate where this curve hits the tangent line. So that's the point that I'm looking for the instantaneous rate of change at. So we need those coordinates, and then we also need the slope of the line. So remember that the slope of the tangent line is the same thing as saying the value of the derivative of f at that particular value of x where the function is tangent. So to find the slope for this linear function's equation, we just have to find the value of the derivative using our limit process. So that is our second task. So we're going to find the value of f prime of 2. So really, to do that, you have two choices. Option 1, we can do the limit definition using the value of x inside of it so that it produces just a number. Option 2 would be finding the derivatives equation using this limit process and then plugging 2 in after the fact. It's technically your choice, but if you have to substitute the value of x in anyways, it's actually easier just to do it right off the bat inside of the limit process. But theoretically, if you wanted to do it the other way, you could. I'm just not going to choose to do it that way. So I want to take the limit as h approaches 0 of f of my c value, or 2. Again, that's the x value at the point of tangency. So f of 2 plus h minus f of 2 all over h. Remember, 2 plus h, that notation or quantity has to be substituted into the function. So when we substitute 2 plus h in, we get quantity 2 plus h squared plus 3 times the quantity 2 plus h minus 1. So all of that is f of 2 plus h, then minus the value of f of 2, which was 9, all over h. And again, this is where we will expand, cancel out any of the non-h terms, and then reduce a factor of h from top and bottom. So expanding the binomial squared gives me 4 plus 4h plus h squared. Distributing the 3, gives me 6 plus 3h minus 1 minus 9 all over h. So now we can go through and clean this up. So constant terms, 4 and 6, that makes 10. Negative 1, negative 9 makes negative 10. So those all cancel each other out. Then I can reduce out a factor of h from everything in the numerator. So that disappears. We lose a factor there. That disappears. And the h on bottom. So what I am then left with is f prime of 2 equals the limit as h approaches 0 of 4 plus 3 makes 7 plus that h that's left over. Now I can evaluate the limit, and I get 7. So again, that value is the value of the derivative at x equals 2, which is the same thing as saying the slope of the tangent line of this function at x equals 2. So we have the slope, we have the point of tangency, so we know that the equation for our tangent line would be y minus the y-coordinate at the point of tangency equals the slope, 7, at the point of tangency minus x minus the x-coordinate. So realistically, if you think about this, when I have a function f of x and I want the equation for the tangent line at the point C with y-coordinate f of c, this equation of the tangent line really takes on the form of y minus the y-coordinate at the point of tangency equals the value of the derivative at the point of tangency times x minus the x-coordinate at the point of tangency. So this is really the format of these point slope lines for the tangent lines. So what this means now is if I go to Desmos and I wanted to graph both of these guys at the same time, so x squared plus 3x minus 1 is equal to, let me zoom back in here, make this guy look a little bit nicer. And now I can actually type our equation in. So we get y minus 9 equals 7 times x minus 2. And if I move up a little bit, you guys can see here they actually intersect at that 0.29. So again, why is this helpful? Well, eventually down the line, we're actually going to use these tangent lines to make really good approximations for the value of these functions near these points of tangency. And you can see there is not much difference right now when you look at it between the red and the black graphs. And that's because that tangent line is a really good estimate for how the curve or what the value of the curve is for points near that tangency point. So the last thing we have to talk about is the idea or the connection between continuity and differentiability. So not every function has a rate of change at every point on its graph. There are certain instances where it's just impossible for us to calculate the instantaneous rate of change of a function at particular values of x. So what we have is a formal definition here of this relationship. So if a function f of x exists such that f prime of c exists for some value of x equals c, then that means that f of x is differentiable at x equals c. So the idea of being differentiable, it really means we can use math to calculate the rate of change or the instantaneous rate of change for the original function at that particular value of x. So in order to be differentiable at a value of x equals c, then the slope of f as x approaches c, it has to be approaching the same value as we move closer to c from both the left and the right side of that value. This is actually where the alternative form for the limit definition of the derivative is helpful. It's actually easier for us to look at this relationship from the left and the right when we use x as x approaches c to control the movement of these 2 points. So again, basically, it's just saying that as you move closer to our desired point from the left and right side, the slope or the tilt of the tangent line, it's going to approach the same thing. Now, for most well-behaved functions, this is always going to be true. Where we get into weird scenarios is when weird stuff happens on the graph. So we're going to take a look at those here in a second. So again, that's the formal definition of being differentiable. The slopes approach the same value on both sides of x equals c. If a function is differentiable at a point, so if this definition is taken care of and is true, then differentiability implies that the function must be continuous at that point. So that's really important. The order there is important. So, oops, actually then wrote the order backwards. So when a function is differentiable, so, or in other words, we can calculate the slope of f. So if it's differentiable, then that is implying that the function must be continuous, because if that first thing is true, then the definition of continuity would also automatically pass. The function would have to be defined there. Can't find slope at a point that is undefined. The limit as the function approaches x equals c, so the y values must be approaching the same thing from both sides, and that limit must equal the value of the function. So it has to be a continuous graph in order for us to be differentiable at that point. But the reverse order of that is not true. That's where we have to get or be very careful. So just because a function is continuous does not also mean the function is automatically differentiable. This is the only order of implication or the logical process that is true. So the reverse order here fails because of a couple possible scenarios with a graph. And we actually talked about these a little bit earlier in the video, but I just want to review and make sure you guys have a formal, clear definition here. So the easiest options for where a function is not differentiable is where case 2 fails. So if a function is not continuous, then there's no way that it's not differentiable. So Easy one here, a hole. If there's no point at x equals c, then there's no way for us to describe the rate of change at x equals c. Same thing is true with asymptotes. If we have a vertical asymptote at x equals c, well, then there's no way that we can describe the rate of change for the function at x equals c. And lastly, the same will be true for breaks in the graph. So the three types of discontinuities that we talked about in previous sections, those would be cases where the function would be not differentiable. Those are the easy cases to point out. The last two, though, these are trickier ones, and these were ones that were mentioned earlier. When a function has a sharp turn in it. So again, these are unique graphs. This one is an absolute value function that I chose to show you. But these sharp turns don't naturally exist. They have to be odd combinations of things for these sharp turns to pop up. But when that happens, the function is continuous at this point at x equals c, but it is not differentiable because this function is making an instantaneous change from a negative rate of change to a positive rate of change. And if the function of f prime is supposed to graph or show you all of those different slopes, if we tried to graph f prime uh, on a separate grid but using these same x values, well, all of these slopes are, let's just say, -1. So it would be -1 slopes, but then all of a sudden we'd have to jump up to +1 slope for the other side. All these values have a positive slope. That can't happen and have the derivative still be continuous and have a defined slope for every point. So these sharp turn examples are where the function can be continuous but not be differentiable, or one possible case. And they're not all absolute value graphs. There are, I like to call these bird graphs because if you're a really bad artist, this is how you draw birds. These are fractional exponent functions. This is a x to the 2/3 power. When we mix in fractional exponents like that, sometimes we can produce these sharp turns as well. Then the last case is something called a vertical tangent. There are some functions where the function is actually going to go vertical for a second. So there are some naturally occurring functions where at certain points where the graph changes what's called concavity, so it goes from like a U shape to an upside down U shape, it does so in a way that the tangent line is going to go vertical for a second. And you can see the graph gets very, very steep, and then all of a sudden it switches over and it continues on in the next direction. This happens with functions like x to the 1/3. This function has a domain of all reals, but when we try to evaluate the slope at these kinds of points, the derivative is undefined and it fails, and that's because we have a vertical tangent line. So anytime that the graph goes vertical at a specific point, we run into these issues as well. So these are the 5 cases of where a function could be not differentiable. We just have to be able to look out for those, and we're going to take a look at a couple examples here on how we do that. Now, for some equations, we're just going to kind of pick up on it, and the mathematical process will take care of itself and explain to us why we can't evaluate the derivative because of the equations we end up with. But other functions like piecewise functions, remember piecewise functions are like Frankenstein equations where we take parts from different kinds of things. Piecewise functions, just like there can be issues with continuity, there can also be issues with differentiability. Because again, if a function is not continuous at a point, then it can't be differentiable at that point either. Since piecewise functions are often not differentiable where the pieces change, they're often, or excuse me, that should be not continuous where their pieces change. They're often also not differentiable there as well. But there are some instances where we need to check or do a little bit further checking there because there are some instances where it is continuous, but we have to make sure that it's not an unnatural sharp turn and that their rates of change make a smooth transition from one piece to the next. So when we check a piecewise function for differentiability, we're going to follow these 3 basic steps. So first, we're going to check the function for continuity because if the function is not continuous, then we know for sure it's not differentiable. We can save ourselves a lot of work. If the function is continuous, then we're going to need to check the value of the derivative for each piece of x equals c. So this is where we would be checking it as c approaches, or we approach c from the left and from the right. If those two values are equal, then that means the graph is going to make a smooth, continuous, and transition where the rates of change are identical at the point of transition. So imagine in a relay race, we want to make sure that in a relay race, when you're handing off the baton, both runners are running at the same rate. That makes an easy, smooth transition when you hand off the baton. If one person sprints past the other one, then it's not going to be smooth. It's going to be unnatural, and things aren't going to work out the way that we want them to. All right, so we want to check the following function to see if it's differentiable at x equals 2. So again, we want to see first, is it continuous? Because if it's not, then we know the answer is no, it's not differentiable. But if it is continuous and we make a transition at a continuous point, then we want to make sure that it's not a jagged corner or sharp turn. So again, just to help you guys visualize what this would look like if it was a bad transition. So we've talked about these transitions in terms of continuity. So we know that if it moves from one point and jumps to another one, then that's a discontinuity. But again, it could make a continuous transition, but not be uh, differentiable for us. So that would be where there's unnatural changes. So again, a natural change, if I want to move from one rate of change to another, there has to be a gradual process that we make that transition. I can't go from being constant and then instantaneously jump up to a very steep slope. There has to be a gradual change within that rate of change. So if this is what the piecewise function would look like, this is a sharp turn. It doesn't mean that not every sharp turn is vertical like this. Sometimes it just means we make a very drastic change from one kind to another without that smooth transition. So what we want it to be, we want it to make it look like it looks like it could be one continuous function without needing these different pieces. So it is pretty obvious when we look at a detailed graph of these whether we have a nice differentiable transition or not. But so for this guy, so again, step one, we're going to check for continuity. So that means what is the limit as x approaches, or excuse me, let's first make sure the function's defined at x equals 2. So f of 2, 2 is included in the domain of the bottom function, so we can plug that in and we get 7. So that is, it's defined. There is a definite point on the graph where x equals 2. Now we want to check the limit as x approaches 2 from the left and right of just f of x. This is not f prime yet. Again, we're still checking continuity. So from the left of 2, this would be the top function. So that would be 8 minus 1 or 7. So that bodes well because we already know what this limit of the bottom guy is because we use direct substitution to find the value of the function. So we know it's going to be the same thing. So this function is definitely continuous at x equals 7. So there is a connected point. There is no break or hole in the graph at x equals 2. So that part of it's good. So the second part now is we have to talk about the rate of change. So on this function, let's try and graph this guy a little bit. So when x equals 2, that's where we're going to make our transition. So to the left of that, we have a linear function. So when we talk about the slope of f, to the left of x equals 2, we're working with this linear function. I don't have to go through the limit process or the limit definition to find the value of this derivative at x equals 2 because, again, the purpose of the derivative function is it tells me this, the slope of f. Well, a linear function, you know what the slope is just by looking at the equation. So when we approach 2 from the left side, I know what the limit of that function's derivative is. Or in other words, we know that as x approaches 2 from the left, f prime of x is equal to 4. We know that again because that is the slope of this linear function at x or when x is less than 2. So that part is done for us. Now, if this was not a linear function, then we would go through the limit definition process with f of 2 plus h and plug all that in. That's what we're going to have to do for this right side. So now to evaluate, I want the limit as x approaches 2 from the right. And we can use the alternative form f of x minus f of 2 over x minus 2. So if you guys want to do it that way, we can. Now it's going to be a more sophisticated process because we're going to end up having to do some extra math in here. But just know that this is the same thing as saying what is the limit as h approaches 0, but we're going to be approaching 0 from the right side. And then we would have f of 2 plus h minus f of 2 all over h. So you can do it either way. You guys have already seen me do it this way. So this time, actually, I'm going to do it with the alternative form just so you guys can see one of those being done. I'm actually going to get rid of this graph for right now until we're absolutely ready to sketch this. So again, to evaluate this, these aren't just placeholder names. They're equivalent to things. So when x is greater than 2, f of x is x squared plus 3 minus the value of f of 2 is 7 all over x minus 2. Oh, and I'm sorry, I forgot my operator. So remember, first attempt should be to try direct substitution. So if I tried to plug 2 in right now, I would get 0 over 0 indeterminate, which means I really just need to continue simplifying this guy. So this becomes x squared minus 4 on top over x minus 2, which really means we can factor that difference of squares, x plus 2, x minus 2, which removes that extra factor. And I am left taking the limit as x approaches 2 from the right of x plus 2. So again, we can do direct substitution with these one-sided limits, but if that is confusing to you, just keep in mind when we evaluate the limit, think of it as a table approach or a graph approach. If I plug in values of x that are slightly bigger than 2, so think of like 2.1, 2.01, 2.0001, we can put all the zeros in there that we want to. The outputs from this function are going to be approaching something, 4.1, 4.01, 4.00000001, and on and on. So that's why we're allowed to just simply still do that direct substitution, because the same concept of approaching these values is true. We're just picking one side of that table to make the evaluations at. So in this case, we also get 4, which, because those two sides match up, means that this is going to be a smooth, continuous, differentiable transition at x equals 2. And to help demonstrate that, let's use Desmos. It'll be a little bit better than whatever I can draw. So in Desmos, when we want to do piecewise functions, we have to establish the domain that they're working on within these squiggly brackets. So I want that linear function when x is less than 2. And again, we know that it's going to stop at 7. And then we have x squared plus 3 when x is greater than or equal to 2. So without zooming out, now if I make these both the same color, you wouldn't even know that that was a piecewise function. It looks like one continuous function, and that all has to do with the fact that this function, these two pieces have the same rate of change from the left and from the right. So if I were to make slight adjustments to this guy, let's say I have 2x squared minus 1. That function is still continuous. I made it so that we still meet up at the same point, but now you can kind of see that it is a little bit steeper. Let's say I did negative x squared plus 11. Right? Now that's a pretty clear, jagged, sharp corner because we went from, again, it's still continuous. I made it so that it meets up at 2, 7 still. But the difference now is this right half has a negative rate of change and it's a decreasing function. So this would be unnatural. This would be a function trying to go from increasing at a constant positive rate of 4 and then instantaneously we switch to a negative rate of change, and that just doesn't naturally occur. So this would be a case where the two limits of f prime of x do not meet up at the same thing. So because of that, we would be not differentiable at that corner or at that value of x. But in this case, both sides do meet up, so we're good. And our function is differentiable at x equals 2.